Hello and welcome to another video. Today we're going to be continuing on with the Blend 75 in TypeScript, and we're going to be doing same tree. So in this problem you're given roots of two binary trees p and q, and you want to write a function to check if they are the same. They are considered the same if they are structurally identical and all the nodes have the same value. So for these two, they are structurally identical and all the nodes have the same value. For this one they are not, because this is the left node and this is the right node, so technically this. So this is the right node of this tree, and this is the left node of this tree, and so these two left nodes are not equal because this is null, this is 2, and this is null, this is 2. And then for this one, they are not the same either because the left nodes have a different value and the right nodes have a different value. Essentially, you're given two trees, and you simply just want to check for two things. You want to check, are all the nodes equal, and do they actually exist, right? So what do I mean by that? Well, let's say you have these two trees and you had something like this. So the values don't even matter here because this tree has these two nodes and these don't exist. So there's two things you have to check for every node. So you have to compare every node of both trees. They both have to exist, meaning if a node exists for one tree, it has to exist for the other. And they both have to have the same value. So we can kind of just like recurse down both trees, like a normal recursion, just whatever you want, any kind of traversal is fine. You just recurse the same way, and then you just check, like, if I have a node in one tree, there has to be a node in another tree, right? I can't have, like, if one of them is null, the other one has to be null as well. So they either have to both exist or they have to both not exist. So for example, let's say we are here for this tree. Let's say this node has value 2, this node has value 2. And we traverse right here into this node. This node exists and this node does not. So this would also have to exist. And similarly, they are allowed to both not exist. That would be fine, right? So if you have something like this, now if we traverse left, this node doesn't exist and this node doesn't exist. That's fine. So they both have to either exist or not exist. And the values all have to be the same, right? So if this is like 1, 5, whatever, anytime you get something that doesn't work, you need to return false. So essentially, you basically recurse, and for a root to be the same, the left traversal and the right traversal have to be true. Essentially, we're just going to return true or false. So the left traversal and the right traversal have to be true, and the values have to match. So let's just show what that's going to look like here for a recursion. So let's actually let's think about this. So yeah, we can just draw in all these nodes, I guess. So let's say we have 3, we have 4, 3, 4, and then this is like 1 and 1 maybe. So essentially, what you would do is you would start at the root for both of them, right? So you just pass in both roots, and you would say, okay, are the values equal? Yes. So if they are equal, you do want to check if the values are equal. It's going to make it a little bit more efficient, because if the values aren't equal, you don't really have to recurse anymore, right? Like if these two values are different, you don't have to recurse. Then you recurse either direction. So let's say we go this way for both of them, and we check, are the values equal? Yes. Okay. Then we recurse. Once again, let's just keep going left. Okay. Are the values equal? Yes. Then we recurse, and we hit two null nodes. So we can just say, like, if both nodes are null, we can just return true. So let's use a different color for a return. So let's say brown is like the return. So we would return true, brown meaning return true, and we would recurse to the right. So that would also return true. Or you could just do that check before recursing. So because these two nodes are equal, they're both not there, and the values are equal, now this part will return true. So we're going to send this up. Now we are going to recurse to the right. We're going to check, are the values equal? Yes, they are. So then we recurse here and here, and they are also equal. They're both null, so that would also return true. So this 5 thing would be true. Then you would recurse back up to the 1, and you would do the same thing for the 2. You would check, are the values equal? Yes. Recurse left, they're both null, so totally fine. Recurse right, are the values equal? Yes. And then recurse left, recurse right, they're both null. So then you would return up, and then these are all, like, you're basically done now, right? The left is true, the right is true, and this root is true as well. So essentially, you're just passing like a group of nodes that would be the left tree and the right tree, and you're just going the same direction. And you have to make sure for every single group of nodes they have the same value, or they're both null, or anything else would be false, right? So if one node exists, one node doesn't, we'll return false, and so on. And we're going to set this up into recursion in a way where if any one of these nodes fails, at the root will be false. Because let's say this node fails, then we will return a true and a false, and we just have to say at this node, the node's values have to match, and the left has to be true, and the right has to be true. So this would return false. This would still return true, but then you'd have false, true. So essentially you're like, this has to be true, this has to be true, and the values have to match. This is false, so this would return false. Okay, so now we can code it up. So we're actually going to do a one-liner here, and I'm going to explain like all of the thought process. And I actually did find something kind of cool in Typescript that I will share as well. So kind of something unique. So first we need to check, is P null, right? So we can just say P question mark, and we're going to have a return before then. And so now we need to check, is Q null? Because if P is true, if it's not null, then Q has to also not be null. So we can say Q, and now we have to remember we have to compare the values. So P.val equals Q.val, and we have to check the recursive thing, right, for the left and the right. So we can do this, the same tree, and then this is P.left, Q.left, and we have to do that for the right side as well, right? So it's same tree for the right side, P.right and Q.right. Okay, so if this is all true, then this will return true, right? So Q is not null, the values are equal, left recursion is equal, right recursion is equal. Now, if P is null, we need to check it, like if Q is null, right? And so if Q is null, or whatever Q is, we need to actually return not Q, because let's say Q is null, that would be false. But we'd actually want to return true, right? If P is false, if P is null, and Q is null, then we want to return true. And similarly, if P is null and Q is not null, we want to return false, which will happen, right? Not an object will be falsy. Okay, but if you notice, if we do this, if we actually test it, we get an error on this case. And another funny thing is if we actually console log P and Q, let's say, and we also console log comparison, and we write this part here, which will be interesting. So you would think that this would return a Boolean, right? It would either be true or false or something. And we are using TypeScript here, but yeah, let's take a look. So you can see here, in this case, we are at tree node 2 and null, and our comparison is actually returning null instead of a Boolean. And so what goes on is, in this operator, this stops whenever one of these is false, but it doesn't return false, it returns whatever it is. So because null is falsy, it doesn't return false, it returns null, which is a problem, right? So we need to make sure that this Q thing is a Boolean, not a null. So we can fix that by saying if Q does not equal null, then we could do this, and that will be a Boolean. And then this part is still going to be fine, because not null will be true and not object will be false. When you use not, you're basically saying it's a Boolean, and this is also a Boolean now. So that is something that you would think this would work. You'd say like, oh, like that's truthy, that makes sense to me, but it actually does not. So now we should be good. Definitely kind of tricky to find, took me a little while, I had to look it up, and something I haven't encountered before, so. Now, if we look, it does work, and it's reasonably efficient, but yeah. So once again, to go over it one more time, we are saying if P is true, if P is not null, then we have to check that Q is not null. If Q is null, just return false straight away. The values have to equal, and the left and right side recursion also have to all be true. And if P is false or null, it will go over here. And then if Q is null, this would return not null, which is true. Or if Q is a tree node, then it will return false, because not an object will be false in TypeScript. You can, obviously, if this doesn't make sense to you, you can write something like this, right? So you can say like something like this, and you could say like if P equals null, if that clarifies things up a bit, that also does work. So just personal preference. Oh, I think it's maybe screwed something up. So I think I actually need p to not equal null here, and then this part needs to be null. Hopefully that's correct. And there we go. So whatever we prefer, totally fine. And yeah, like I said, around the same. So pretty much everyone's going to have the same solution for this one. So let's go through the time and space for this one. So for the time, we essentially are going to recurse through the entire tree for both of them. But one tree can technically be bigger than another, but as soon as we run into an error in one of them, we are returning false. So I'm just going to say O is O of n, where n is the length of, I guess if they're like the same sizes, worst case, it would be kind of hard to say, but I'd say roughly it's the size of like, yeah, if they are different, the first node that's different is going to be false. So I would say it's something like the size of the smaller of the two trees. So if you have like A and B, it would be the size of the smaller one. Because if you think about it, when you recurse through this first tree, you're going to start running into nodes that exist in one tree and not in the other. So you're only going to have true values while you have nodes that are in both. And the space is going to be the same thing, because you can technically have like a recursive call stack that, let's say all of your nodes look like this, right? As always in these tree examples, if all your nodes look like this, then you will recurse all the way down all of the nodes of the tree, if they're just completely unbalanced. But on average, it will be log of the minimum of the trees. And so that's going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.